we will prove the following theorem. If fn converges f pointwise on a closed interval, and each of the fn is differentiable with f prime of n going uniformly to g on the interval, then two things. F is differentiable and f prime equals g. And the big picture of how we're going to prove it is right here. So basically let epsilon be bigger than 0 and c be any element of there. We're going to prove that f prime of c is equal to g of c. So we're going to let delta be something that I'm going to fill in later. This is big picture right now, so I don't need to give you all the details. And as long as x is within delta of c and x belongs to the interval, this thing minus g of c, remember we're going to prove that g is equal to f prime. So you think of this g of c as being, sorry, I want to be that a different color. Think of this g of c as being like an f prime of c, because that's what we're going to prove. We don't know that's f prime at this point, but that's the way you're thinking of it. And this just comes from the definition of derivative. If this thing is less than epsilon, we're going to be good. So how are we going to do that? Well, we're going to do it by using the triangle inequality. That should be a strict inequality. And to do that, we're going to just split this up by adding and subtracting a couple different things, the usual way. And you'll see that right here you have f sub n, big N. That's going to be a fixed function that I have not yet defined. So I'm marking that with pink to indicate that I need to tell you what it is. Similarly, its derivative has to be defined. So basically, this is the big picture. This thing, which is basically the definition of derivative, will be less than epsilon. Less than epsilon. But I have 5 things I need to tell you. Actually, it's going to be 6. 1 red, 1 pink. I need to show that this thing is less than epsilon over 3, the blue thing is less than epsilon over 3, and the purple thing is less than epsilon over 3. And I'm going to do this with probably a series of podcasts and a bunch of lemmas. All these lemmas are going to be basically the situation in this proof. So I'm not going to go and rewrite all of it. But I will say, I'll color code these. This lemma is going to prove that this thing is less than epsilon over 3. So I'm going to prove that fx let me try that over again. I zoned out for a second. Fx minus fc minus f sub little n of x minus f sub little n of c over x minus c. It's going to be less than epsilon over 3 for all n bigger than or equal to an n1 belonging to the natural numbers to be named later. To be named later. So in the proof, right? In the proof, this is not very good form for lemma. This is very much shorthand. Proof is, if I look at this thing, well, what I can do is I can let h of x, wait one second. Okay, I just erased something because I screwed up a little bit. Actually, I want to erase a little bit more. So for the proof, what we're going to do is we're going to let m and n be any 2 natural numbers. Any 2 we want right now. We're going to restrict them later. We're going to define an infinite number of functions, m comma n of x, equal to f sub n of x minus f sub n of x. Then I'm going to apply the mean value theorem. After I fix any x belonging to a, b, by the mean value theorem on either cx or xc, whichever one makes sense, I get there exists an alpha belonging to, let's just say cx, such that f prime of m of alpha minus f n of alpha prime equals a quotient that I'm going to tell you in the next screencast because I'm just about out of time. So I'm going to stop here.